Okay, let's look at another example. So use polynomial method to determine the eigenvalues for the matrix A. Now obviously this matrix A is actually the coefficients of a system of linear equation, yeah? Okay, then find the corresponding eigenvectors. Perform your calculation in 4 decimal places. Alright, so our first step is you want to find the eigenvalues, and finding the eigenvalues means you introduce lambda into your diagonals, yeah? So our A take away lambda I. So we are calculating matrix A take away lambda I. Right? So that would be 2 take away lambda minus 1, 0. That's the first row. The second row is entry minus 1, 2 take away lambda minus 1. And the third row would be 0 minus 1, 2 take away lambda. Alright, so lambda would be our eigenvalues. So how do we calculate our eigenvalues? We have to find the determinant of that matrix. Okay, so next step, we want to find the determinant of A take away lambda I. Alright, now if you recall in our earlier lectures, yeah, we have learned how to calculate the determinant. So let's say in this case, I am referring to the first row. Okay, so the first row, which is there. Right? So if I am referring to the first row, the first entry is 2 take away lambda. Yeah, that's the entry. And we multiply, yeah, so let's just recall this, yeah. If we are referring to that entry, so we temporarily close the column and row with that entry. So now we are finding the determinant of what is left. Okay, let me just write this down. So times with 2 take away lambda minus 1, 2 take away lambda. Okay, so that is for the second entry, first entry. Now for the second entry, minus 1. So our entry is minus 1. Okay, so we are referring to minus 1. That means we temporarily eliminate those lines, line and column. Okay, so what is left here is minus 1, 0, 2 take away lambda. Alright, for the third entry, that is 0, so I'm just going to leave it at that. Now this would be equals to 0. Okay, note that I don't have the sign in between the terms. Okay, if you recall, the sign for the first entry, this is positive sign, negative and positive sign again. So you add that in your calculation. Now, so the first one is positive, I don't have to write that down. So this is going to be negative, and the third one is positive. Okay, now let's solve this. So 2 take away lambda. Let me just bring this up. Right. So 2 take away lambda. So let's multiply that. Okay, so that's going to be 2 take away lambda times 2 take away lambda, take away minus 1 times minus 1. Alright, so negative times negative, that's a positive. So this is going to be minus 1 times 2 take away lambda, take away 0. That will be equals to 0. Okay, let me just write 2 take away lambda out here. Alright, now expanding. Okay, so now this becomes, let me just check. Okay, so this becomes 4 take away 4 lambda plus lambda squared, take away 1 Alright, so minus 2 plus lambda equals to 0. Okay, so you simplify the function inside the square bracket. So now I have lambda squared take away 4 lambda plus 2. This is equals to 0. So now how many eigenvalues will you get here? So obviously we are solving 3 simultaneous equations, yeah, in our linear system. So therefore the maximum we can get will be 3 values of eigenvalues. So the first one is lambda equals to 2. That's our first lambda. Alright. The second and third lambda would be obtained from here. Okay. So you can use your calculator or you can use the formula for finding roots. Yeah. So now I have my lambda 2 as 3.4142 and our lambda 3 equals to 0.5858. So we have 3 lambdas here. That means you will have 3 corresponding eigenvectors. Okay, so let's do the first one. So the first one is lambda equals to 2. So what you do is you insert the value of lambda equals to 2 inside your equation. Yeah, insert it inside here. Right? So if I do that, this is what I have. Okay. So now I have 0, minus 1, 0, minus 1, 0, minus 1, and 0, minus 1, 0. Okay. I repeat, where do I get this? It is just inserting lambda equals to 2. Yeah, that value, lambda equals to 2, inside the function there. Okay. So this is what I have. Right. Next, multiply by x. The same steps as we did just now, yeah, in the previous examples. Right. So that would be equals to 0. Okay. Now we want to find the values of x. Right? If you recall, in Gaussian elimination, it would be better if we can transform this into upper triangular form so that we can use back substitution. Now, if you recall again, we are allowed to do 3 operations, which is interchanging, scaling, and I forget the third one. Okay? Now, let's say I am interchanging row 2 and row 1. So let me just write it here. So row 1 interchange with row 2. Now why do I do that? Because we do not want 0, A11 as our first entry. Alright? So we are doing interchanging here. That will be minus 1, 0, minus 1. Okay, so now our row 1 becomes row 2. So that's going to be 0, minus 1, 0. And 0, minus 1, 0. Okay. Now, for upper triangular system, we need to reduce that into 0. Okay. So what we do here is, in the next iteration, so our row 3, we just do the calculation of row 3 take away row 2. Okay. And this is what I have. So the first 2 rows are taken as pivot rows now. Right? Taking those 2 away would be 0, 0, 0. So now we are going to do back substitution. Right, supposedly from the last equation you should be able to find your x3. But in this case, all values are 0, therefore we cannot find x3. Hence, we have to make an assumption. So let us just let x3 equals to t. T is an arbitrary independent variable. Yeah, let me just put here. T is an arbitrary independent variable. Okay. All right. So what does arbitrary means? Okay, it means that now you can have various values that may be assigned to this, but remains unaffected. Yeah, but it remains unaffected. All right. Let us say x3 equals to 3. Now we can use back substitution. Let's move there. Okay. So if x3 is equals to 3, we apply into our second row, which is there. All right. So from the second row, we have minus x2 equals to 0. So that means our x2 value would be equals to 0. Next, you need to find your x1. Where do you get that? You back substitute into the first row. So from the first row, I have minus x1. Okay, take away x3 equals to 0. x3 was t just now. So minus x1 take away t equals to 0. x1 equals to minus t. So therefore, you can have our eigenvector here. Alright. So the values would be x1 is minus t, x2 is 0, x3 is t. Okay. So the next step, we bring out our t value. T is arbitrary, yeah? So we bring out t. So what is left is minus 1, 0, 1. Okay? Now, at this stage, which one is our eigenvector? So you have to normalize first. So normalizing, which means what? We divide with the entry that has the highest absolute value. So we refer to these entries. Which one has the highest absolute value? Okay. For entry, the first entry and third entry, both has the same absolute value, isn't it? So let us just take as minus 1. So therefore, our x values all must be divided by minus 1. So our calculation, yeah, everything divided by minus 1. So minus 1, 0, 1. Okay. So therefore, after normalizing, it becomes 1, 0, minus 1. Alright. So this is our eigenvector, which corresponded to the eigenvalue lambda 2. So let me just make a conclusion here. So therefore, for eigenvalue lambda equals to 2, the corresponding eigenvector is 1, 0, minus 1. Alright. So now we have to do for the next two lambdas. Okay. So for our lambda 2, the value is 3.4142. Right. So we do the same thing. Insert our lambda into our equation. Okay. So what I obtain is, the first entry is minus 1.4142 minus 1, 0. Okay, these are the values when I have taken away lambda, right? So minus 1.4142. Right. So multiply by x. That will be equals to 0. Okay. Now reduce that to upper triangular system just as we've done before. So I'm just going to write here. So reducing to upper triangular system. Okay, so what is left is minus 1.4142. Yeah, so the same, the first row is being taken as our pivot row. The second row is going to be 0 minus 0.7071 and minus 1. Let's shift this a bit. Okay, and the third row is going to be 0, 0, 0. So let's not just write the x there, let us just write in augmented form. If you recall, augmented form is whereby we temporarily eliminate x and just include one more column with the values b. Okay, now in this case, it's the same as before. We cannot find x3. Therefore, we let x3 as an arbitrary value. Let's say that equals to t. Right? Okay. Now use that back substitute into our second row. So that means minus 0.7071x2 take away x3 equals to 0. So our x3 is equals to t. So x2 will be equals to t divided by minus 0.7071. Okay, so therefore our x2 is equals to minus 1.4142t. Okay, so the same steps, you insert x2 and x3 into our first row. I'm just giving answer here. Our x1 is equals to t. Okay, so now our solution. So therefore, our x now becomes t minus 1.4142 and t. So I'm bringing out the t. So 1 minus, sorry, I left out t there. So 1.4142. Alright, we factorize out t. Okay, so now if we divide by the, we are normalizing, that means we divide with the entry that has the highest absolute value. Which one is that? Okay, so let us just look here. So the absolute value for the first one, okay, that is 1. The absolute value for the second entry, that is 1.4142. Okay, and the absolute value for the third one is 1. So which entry do we choose? We would choose the second entry. Now note that what would we divide would be the entry, yeah, not the absolute value. That would be the entry. So therefore, our next step, right, if we let our arbitrary t equals to 1, okay, then let's shift this up a bit. Right, so then our x now divide by the entry, which is 1, over minus 1.4142, and we divide to all entries 1. Right, so therefore our answer is going to be minus 0.7071, 1 minus 0.7071. Okay, so for lambda equals to 2, right, the eigenvector is going to be minus 0.7071, 1, and minus 0.7071. Okay, so that is the second eigenvalue. Let's look at the third eigenvalue, the last one. So I'm going to go a bit fast here. So for the third eigenvalue, which is 0.5858. Alright. Now, inserting that lambda inside our equation, so what we have is 1.4142 minus 1, 0. So minus 1. Okay, let me just write all the entries here. So this is just simple calculation, yeah, whereby you insert your lambda inside our earlier equation. Okay, so now I have this. Straight away into augmented form. Okay, next step, we reduce to upper triangular system. Let me just write it here. So next step, so we reduce into upper triangular system. Okay, so you can use elementary row operation. So what I have here is, we make the first row as pivot row. That means we are fixing that. Yeah, we are not changing anything towards that. That's our first row. So our second row, okay, and the third row, this is using Gaussian elimination. We obtain all 0. Okay, just as before, we let our x3 to be arbitrary, equals to t. So back substitute into the second row. So 0.7071 of x2, take away 1x3 equals to 0. So our x3 is equals to t. So therefore, our x2 is equals to 1.4142 t. Okay, so once you have that, x2 and x3, we back substitute into the first row, and we found that our x1 is equals to t. Okay, so the same steps. So now, our vector x becomes 1, 1.4142, that's our x2. Our x3 is t. This is where I've already bring out our t value. Okay, so we can't stop here. You note that, if you recall, I did mention earlier on that all the entries, if it is normalized, all the entries must be 1 or less. Yeah. So in this case, the highest entry with the entry with the highest absolute value, that will be 1.4142. So you have to divide, normalizing, you have to divide by 1.4142. So normalizing, so now our x divide by 1.4142. Okay. So therefore, our final eigenvector, that will be 0.7071, 0.7071. So this is the eigenvector which corresponds to lambda equals to 0.5858.